Hey, Dr. Boyer, I got my sunglasses on.
All right, cool shades, man.
Yeah, you know, we're studying light today.
Yeah.
And light's kind of cool.
Yep.
But you kind of, you know, when I look up at the stars, it doesn't work very well.
No, I think you need something better than sunglasses to see the stars.
But before we learn about the stars, we got to figure out what you study when you study the stars.
I know. What can you study with us just looking at a star?
Well, I think it's light.
It's light, exactly.
We have to look at light, and so today we're going to talk about what is light. So kind of the funny thing is when you look at stars, all you can see is
light.
Yeah, light.
That's it.
I think that's all there is.
Wow.
So there's so much science to light. So this whole chapter 3, guys, is all going to be about about light. We're not going to spend a whole lot of time talking too much about astronomy, but just about light, so that we can understand later on astronomy.
Exactly. How do astronomers figure out what's going on out there?
So podcast 3.1, we want to talk about, light and what light is.
Yeah, what is it?
Well, you know,
Mr. Bergmann, explain this to me.
Well, it has properties.
Yes, okay.
You know,
like what?
Well, lots of other things. Let's talk about that. Well, first of all, light comes in colors, and you guys know this, right? White light comes through, and it hits this. What is this triangular deal?
That is a glass prism.
It's a prism. I think I spelled that right.
Yep.
That's a prism, and it splits light. So this is white light. Something you may not know is that white light is a mixture of all the colors of light. So when it hits the prism of light, it breaks apart into some colors. We would actually say Roy, G, Viv. Red, orange, yellow, blue, green, blue, indigo, violet.
There they are.
That is the colors of light that the human eye can see.
Yes.
Turns out there's more light than you can see, but that's what you can see. Okay? So, let's talk some more about this. So, why should we study light? I guess we kind of already addressed this, but...
Well, if you want to know what's out there in the sky, you have to see the light that comes from it and study it.
Yeah, so all we can do is you got telescopes or your naked eye or whatever. You've got devices that look at light. So that makes sense, right? So, so what is it? Well, here's a bunch of things, but I want to copy this down. So what's the speed of light in a vacuum? Now wait a second. So light travels at a certain speed.
Oh, yes it does.
So that'd be one of its properties.
It is
so it
not
travels at a certain speed.
It is not.
And it's a constant, and it's denoted by the letter C.
Yes, little c.
Little c. Big C means something else in science land. So, by the way, that travels, by the way, C is equal to 3.0 times 10 to the 8th meters per second.
Whoa, that's fast. Whoa, how fast is that anyway?
Well, that doesn't make a whole lot of sense. Could you put that in miles per hour for me, Dr. Boyer?
It's about 185,000 miles per hour.
185,000 miles an hour?
That doesn't help a whole lot. That's still, I don't understand how fast that is.
So light travels at a certain speed.
It does.
So for example, folks, if light that left the sun traveling at 185,000 miles an hour takes about, is it 8 minutes? I want to say it's 8 minutes. Something like that. 8 minutes?
8 minutes.
8 minutes for the light to get to the earth. So if you go and you look outside today and you see the sun, you're looking at 8-minute-old light. If you go look at some stars, you'll be looking at 1 million or even 1 billion-year-old light. You're looking into the past. Very cool stuff.
Yep.
All right, so it travels very fast, okay? But it is reduced as it passes through it. Transparent materials, what do you think that means, Dr. Boyer? What's up with that?
Transparent material is any kind of material that you can see through.
Okay.
So glass is an example.
Glass, like the glass prism. Right?
That's right.
Okay.
But as light passes through a transparent material, it slows down.
Okay, so this speed here
Whoa.
is not the speed it always travels. It changes its speed.
It depends upon the material it goes through.
Okay, so like it travels through water, guys, which is a transparent medium.
Yep.
It's going to slow down too. I don't know if you've ever been at the swimming pool and somebody was sitting in sort of calm water and you look down at their legs and they looked all short and stubby. That's because light slows down in a transparent medium and it bends the light, something called refraction.
Yep.
It's pretty cool. Okay. And it's dependent on the color. So
Yes,
what does that mean there? Transparent appears to depend on the color.
What that means is that the color of the light, remember blue and green and yellow, those colors that have,
The color that you have determines how fast it goes.
So some goes faster than others.
Yes.
In the transparent medium.
The more purple the color,
okay,
the faster it moves through the medium.
So the purple stuff goes faster.
And the red goes the slowest.
That's only if it's in the transparent medium.
That's right. Now, light does go through other mediums, but we're not going to worry about that. We're going to stick to transparent mediums.
Yeah. And this is the fundamental reason the telescopes work the way they do, because of the differing speeds of the light through a transparent medium. Because if you think about a telescope has a lens and also mirrors. We'll talk more about that in the next chapter. They've got lenses and mirrors, which are transparent mediums, particularly lenses, and that's going to cause the light to bend and bend at different amounts.
That's according to its color.
According to its color.
That turns out to be a problem.
All right. So let's talk some more about light. Light is a wave.
It is.
So it's a wave. It travels as a wave. A wave? What the heck's a wave, Dr. Boyer?
Well, look at this thing right here. I love this.
A wave.
I like this picture. This is a picture of light traveling along through the vacuum of space. And it turns out there are two pieces that make up the light. There is the electric part, and then there is the magnetic part. And they're perpendicular to each other. Light is a weird thing. So
there's like two waves to light?
That's right. There are two waves here that are traveling simultaneously. You've got the electric and you've got the magnetic, and they travel together as a pair, as a partner, as they move through space.
And so we actually call light something different. We've been using the word light here, guys, and let's actually use the more scientific term.
Yes, please.
And that scientific term is this: electromagnetic radiation. Because one thing we haven't said, folks, is that when you think of light, you think of Roy G. Biv.
That's right.
But there's more light than that.
Oh, way more.
There's radio waves, there's microwaves, there's gamma rays, etc. And we'll talk about that in a couple of minutes. So, but yeah, so there's two parts: the electronic. How do you say it again?
Electrical.
The electrical part and the magnetic
part. Exactly.
Okay. So let's talk some more about this. Okay, but light. Oh, did I skip a slide?
There we go.
Light can also be described as a particle.
Wait a second. It's a wave. It's a particle?
It's a particle too.
What is it?
Well, I don't know. Is it a particle or a wave?
It's both.
So it's also a particle. When you think of a particle, when you think of a baseball is a particle. It travels in a straight line. Okay, so if you throw the baseball, well, gravity might affect it or whatever, but it travels in straight lines. Okay, if it hits a wall, it's going to come back at the same angle, etc. There's a lot of things that are true about particles. You might almost think, probably should have put a picture maybe like of a billiard table. When you think of a billiard table, you think more of particles than I'm thinking.
Yep.
So, but anyways, yeah. So it's also a part. So it's both. So light is thought of a stream of particles called photons.
Photons. Yeah.
Photons.
Photons.
What the heck's a photon?
What the heck is a photon?
I don't know. I'm talking about a photon.
Photon is a packet of light.
A packet of light.
I know.
So I buy packets of food.
Yeah, in fact, physicists call this a wave packet. Just to recognize the fact that sometimes it behaves like a wave and sometimes it behaves like a particle, which we call a photon.
Okay.
And that's how it works.
So the particle, the baseball of light.
Yes. Baseball of light is called a photon.
Okay.
Yeah.
I get that. That makes sense to me. Okay. All right. So there we go. So which one? Hello. So which model do we use?
Well, we use it depending upon what we're trying to observe.
So it depends.
It depends.
So sometimes we like to think of it as a wave, and sometimes we like to think of it as a particle.
Exactly.
Okay. All right. So in a vacuum, photons travel in straight lines.
And behave like waves and particles at the same time. This is weird. Oh, this is even more interesting.
Subatomic particles behave as waves?
That's right.
Wait a second. What's a subatomic particle?
Oh, well.
Sub means like underneath, like submarine.
Yeah, these subatomic means things like protons.
Oh, protons? Oh, yeah, like in the atom. There's protons.
And electrons.
Oh, yeah, those little tiny electrons. It whizzes around the nucleus of the atom.
And even the stranger, the neutron, these things are all subatomic particles, make up the atom, and they behave like waves. You believe that? They do.
In fact, guys, here's something that's going to blow your mind. Everything behaves as a wave.
Yeah. Even
the
you.
baseball, even you.
You are a wave too.
So when you throw the baseball, it's actually moving through space like this.
You don't see it, but
Yes.
it does behave that way.
But it turns out that that wavelength, we'll talk about what that means when I say the word wavelength, is so small it doesn't matter. But for an electron and a proton and a neutron and light, it's a big deal.
It is a big
It's a
deal.
high percentage of its issues, okay? So, yeah. So this is called the wave-particle duality. All particles of nature behave both as waves and particles.
It does.
Everything. The
Everything.
baseball, you. But where it makes a big difference is with light.
Yes.
And also with electrons, protons, and neutrons. But for light's the key thing. Okay? All right. So let's finish this up here with a couple more things. Which property light manifests itself depends on the situation.
That's right.
But for our folks, we've been talking about all this wave-particle duality, and it's kind of crazy. The reality is that when you're looking at it from an astronomical perspective, we're going to focus on the waves.
The wave
The
particle.
particles are cool, and others branches of science are going to be more interested in that. But waves.
Waves is what
So
we
we're going to
want.
focus on the whole wave thing. So, well, we're going to talk about waves. Oh, forgot. We gotta
Oh, yeah.
No one told me that I was going to have to work with her. Of course, you get this. This is a wave.
Wave
And this is
and
a
a
particle.
particle. And this gentleman here in the chair.
Oh, yeah, I forgot the.
This gentleman is a German physicist, Schrödinger. He was the one who said, whoa, these two are the same.
Yeah, it was pretty crazy.
Yeah.
Schrödinger
When he came up with this, people thought, oh, it cannot possibly be. But he was right.
He was right. So he kind of a crazy dude. Okay, he figured it all out. Okay, so let's talk about light and color.
Ah.
Okay, so first of all, what's the difference between different colors of light? I know that red and there's green and blue. I can see that with my eyes. But I kind of see something different with these waves.
Looky here. Look at. Ooh. All right, now look at these different waves, and what you see here is
Yeah.
that the distance between these two crests is different than the distance between these two crests, between these two crests, and these two crests.
So the top of the wave is called a crest.
Yes.
First of all.
And this distance right here is called the wavelength. And wait a second. This is a weird character. This comes from the Greek alphabet.
It's the character lambda.
Lambda. It's the little Greek letter L, and it represents in physics wavelength, the distance between crests of a wave.
Crest to crest.
Yeah.
Well,
but-
wavelength, that makes sense. The length of a
wave. Yeah.
Okay.
Now, notice that as you go up to the colors red and green and violet, the wavelength is getting shorter and shorter. And that's how we distinguish between the colors.
All right.
What's the wavelength?
So the key thing, guys, to understand is that the wavelength determines the color. So purple has the shortest wavelength of visible light, and red has the longest wavelength. So it's how long the wave is.
Well,
It's
how
really-
long is the wavelength anyway?
Well, I bet we should look at that.
Yeah.
Let's see what that is. Okay, so colors, which the human eye is sensitive, is referred to as visible spectrum. By the way, we said there were different kinds of light,
Yeah.
Roy G. Biv, but those that our human eye can see are in the visible
Just the
spectrum.
visibles. Now, we need to take a look at these other wavelengths of light.
Yeah, so these other wavelengths of light. So let's take a look kind of at...
Lambda, this fancy character right here, is what we use in physics to just denote the wavelength of light.
See, what happened is, there's all these symbols that are C for the speed of light.
Yeah.
There's all these other symbols. Basically, scientists ran out of letters. When they ran out of letters, they started going to other letter systems. So they went to the Greek system. So that's why we have these funny symbols like lambda and stuff. Okay. So it's measured in something called a nanometer. Now,
Whoa.
what the heck's a nanometer?
Nanometer is a really, really
Nano.
small.
I've heard the word nano before.
Nano, yeah, nanotechnology.
Yeah, yeah.
So small you can't even
So
see.
nano means small.
Yes,
Well,
and
not
it's
really.
so small that it's 10 to the minus 9 meters.
10 to the minus 9 meters. So that means...
What does that mean, Mr. Bergman?
That's like point. All right, so that's what's this? 0.1, 2, 3, 4, 5, 6, 7, 8,
And a 1.
and a 1
Whoa,
meters.
that's small.
Now, a meter, guys, if you're not familiar, a meter is 3 feet-ish, a little over 3 feet. So take that and divide it into 1 billion pieces,
That's right.
and that's a nanometer.
Whoa,
So we
that's
measure in a unit called a nanometer because wavelengths are really, well, short.
really short for
At
the
least,
visible.
at least
yeah.
for the visible. So they're very short, and so that's why we use such a small number. So turns out that red light is about 700 nanometers, and violet is 400. And so everything in between
Is visible light.
is visible light.
That's
So
what we see.
all your eyes can see, the human eye can only see from 400 to approximately 700 nanometers. If for some reason it's like 380,
Don't see it.
you can't see it. Or if it's 1,000, you can't see it.
Nope.
But it exists. There
It's
is
there.
light that has 1,000 nanometers. But your eyeballs, well, they can't see it. Some critters, insects can see in the infrared, I believe, and
even the
in the
ultraviolet.
ultraviolet.
Yeah.
So different animals can actually see in different wavelengths that we can't even see, which is kind of a wild thought.
It is.
Okay, so
There we
this
go.
is just kind of a breakdown of some of the colors, which we already said 700 to 400. But if you want to see yellows, 580, and blues, 480. Okay. So let's take a look about waves. There's parts of a wave, right, Dr. Boyer?
That's right.
So why don't you talk to us about the different parts of a wave? You've already alluded to one of them.
Oh yeah. First of all, we've got our wavelength right here. The distance between two crests.
All right, top to top.
Top to top.
Maybe we should label what a crest is. What's the word? Just
Crest is where the wave is at its top right here. And then we sometimes call these the troughs right here.
All right, so let's do that. So troughs down the bottom. Why don't we label the top of the wave for crest for that?
Okay, there we go.
So that's the crest, okay.
And so the distance between two successive crests, or the distance between two successive troughs, is known as the wavelength of the wave. And it doesn't make any difference how you measure it, it's the same. And same thing down here.
Okay.
Yes.
So we've also got down how tall a wave is.
Yes.
So how tall a wave is, the wave is this tall from here to here, and that's called
amplitude.
amplitude. So that's how tall the wave is.
That's right.
To kind of give an analogy, folks, on that, amplitude is like, you've ever heard of an amplifier? Another wave that you're probably familiar with is sound. And if you have an amplifier that amplifies sound, and you probably do for your stereo system, is that you turn it up. When you turn it up, you're increasing the amplitude. It doesn't change the wavelength of the wave, it just changes the amplitude. It makes it louder.
Makes it louder.
Or in the case of light, it would make it brighter. Okay? And also on this wave, we've also got the waves are traveling. And so they travel with a specific velocity, which we could say equals v, but since we're talking about light, we could say equals c, which is the speed of light. And there's also something called frequency, which we're going to talk about in just a minute. Okay? All right. So let's talk about the visible spectrum here. So,
Whoa, look at that.
now this is an interesting diagram right here. On this diagram, we have, well, what is this, Dr. Boyer?
This is the complete spectrum of light. All the way from here to here and beyond each direction is the full electromagnetic spectrum of light. And notice the only thing we see is just this little teensy-weensy piece. In fact, on this diagram, this has actually been blown up. It's actually much thinner than that.
Yeah, it is.
We hardly see anything in the electromagnetic spectrum.
So, folks, this is like all the light that exists. Remember we said it a little bit earlier, that what your eyes can see is from 400 to 700 nanometers. This is what your human eye can see, assuming you're colorblind, I guess, or whatever.
Yep.
So this is what you can see, but it turns out that if you make the wavelength a little bit shorter, all right, then you get UV, ultraviolet.
Oh.
Shorter yet, it's an X-ray. Shorter yet, it's a gamma ray. That little Y is a gamma ray. If you make them a little longer than visible light, it's infrared. A little longer than that, it's a microwave. Longer than that are radio waves. We can just call this whole group radio waves.
Yep.
So it just changes the wavelength. And notice on this chart here is that we've got this funny symbol lambda that Dr. Boyer was talking about. That's the wavelength. So the wavelength of visible light, this is in nanometers, but we might just say this is also 10 to the minus 7th. 7 zeros and a 1. Actually, 6 zeros and a 1. That's what we can see. But if you make it shorter, 10 to the minus 10th, that's how you get X-rays. And gamma arrays are like 10 to the minus 14th. Radio waves, by the way, are actually quite long.
Oh, they are. Look at that.
10 to the 4th. That's 10 to the positive 4th. That's 10,000.
It's 10 kilometers. Wow.
10,000 meters.
Meters.
That's a long ways. I ran 10,000
That's a
meters
10K
the other day.
race. That's over 6 miles.
Yeah, I ran that. It took me 50 minutes the other day when I did that in a race. So it's, yeah. So this is all the lights. Your eyes can only see this much, which is not much.
Not much at all.
And in reality, is just we can't see all of light. Not all, no critter, but actually we can detect them with our detectors.
Yes.
And actually we can create, as we'll talk about later, telescopes that can see in these invisible
Everything.
spectrum.
We can see it all.
Yeah. All right. So, as we kind of already said, red light has a longer,
Yep.
and purple light is shorter.
Shorter
the
wavelengths,
So
yep.
we kind of saw that in the pictures, but just kind of give you a perspective. Okay, frequency. So
Ah.
frequency, you can also measure something called the frequency of light. It is sometimes more convenient to talk about as frequency. So if we go back, okay, well, actually, it's a number of wave crests that pass a given point in a second, measured in something called
Hertz.
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 Okay.
Oh, Hertz.
Yeah, talk about Hertz.
Yeah, Hertz was a German physicist, and he did a very important experiment. He was the first one to create broadcast electromagnetic waves, on which everything we do today is based. So
Broadcast. So you're saying that when I turn my radio on, that's light?
yes, it is. When you turn your radio on, it receives light, and when you use your cell phone, it receives light and sends out light. It's amazing. There, you got one right there.
So my cell phone right here, guys, it's receiving light right now. It's receiving actually microwave radiation. And so when I get a text from one of you maybe, that text, I get light into here, and then it transfers into like a text. But it's light, yeah. Isn't that kind of weird? It's light you can't see with your eyeballs.
Oh, but the phone can see it.
But the phone can see it. So
Yep.
it's a little detector for light, for a specific wavelength or frequency of light. By the way, the unit on a wave crest, or a frequency, is going to be in waves per second. Or sometimes we say
Cycles per
1
second.
over second, okay, or cycles per second.
Cycles per second.
Waves like cycles.
However you like it.
And, or sometimes this would be kind of confusing. They say seconds to the minus 1. That is kind of the inverse of seconds. Okay, we'll kind of see that in a little bit. Okay. All right, so there's actually an equation. So we're going to get some math. We need your calculator a little bit. And that is that, now this is a kind of, we didn't write this very well, is that the velocity of the wave times lambda, we wrote L because my computer can do that, is equal to c, where c is the speed of light. No, this is frequency.
There's that one of the, doggone it, those scientists, they're using another character.
Yeah.
This is the little Greek letter N, and it stands for frequency.
So N stands for frequency?
Yep.
Why didn't they just choose F?
Well, we do use F.
But it got used by somebody else.
It got used by somebody else.
Yeah, so they had to go to the Greek language.
So there we go again. So frequency times wavelength gives you the speed of light. This is a really important equation.
You guys might want to just think of it as F lambda equals C, where F is frequency.
That works too. I
as
like
long as
it.
you know that, but reality is that scientists have chosen the Greek
Oh,
language.
that's right.
So, yeah.
Makes
life
it look
in the
more
vast land.
important.
Yeah, maybe that's what it is. Okay, and we've discovered, of course, long wavelengths have low frequencies, and short wavelengths have high frequencies.
Exactly.
Let's go back to that chart that we had a minute ago.
There it
If you
is.
look at this chart, guys, if you look at the short wavelength, this is a gamma rays wavelength, right? This is wavelength. It's 10 to the minus 16th. That's really small, guys. But the frequency is 10 to the positive 24th. That's a big number.
Woo!
10 with 24 zeros. So the higher the frequency, the lower the wavelength.
That's right.
It's an inverse
And
relationship.
if you multiply those two together, you get the speed of the light.
Yeah, exactly. And which we're going to do in just a minute. So, all right. So let's watch a short video clip about frequency.
All right.
All right, today I want to talk about frequency. Frequency. Now, in a wave, the frequency is the number of waves that hit per second. Now, the way I want you to kind of visualize is pretend that I'm standing at the ocean. So if I was standing at the ocean and the waves were hitting my feet, okay, with a certain frequency. So let's pretend that these pieces of cardboard are actually waves. And so let's kind of listen to how it would sound. So one frequency, they would be hitting the waves like this. Hit, hit, hit. Now that's kind of a relatively low frequency. But if I had a higher frequency, I would have more waves hitting me per second. And it might sort of sound, if you will, like this. Hit, 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 hit. Okay, now with a light wave that travels at 3.0 times 10 to the 8th meters per second, the speed is the same. So if you have a shorter wavelength, you will have a very quick frequency. And if you have a longer wavelength, you will have a shorter, or a shorter frequency. Okay? Or actually, a less frequent hitting of the waves. Okay? So that's what frequency is. We're going to do some sample problems. Okay? So, question number 1. What is the frequency of light that has a wavelength of 5.4 times 10 to the minus 11? We probably should write that out. It's 5.4 times 10 to the minus 11th meters.
Ooh, that's a short wavelength.
That's a really, really short wavelength.
All right.
So, Dr. Boyer, how did we solve that problem?
Okay, we got to use that fancy formula.
That
we had.
equation. Let's use the F, I think that might
So
be.
let's use the F. Frequency times wavelength gives us speed of light.
And I know what C is. That's 3 times 10 to the 8th meters per second.
That's right. And in this case right here, guess what we just know?
Well, that's going to be
That's our wavelength.
So I know 2 things.
That's right. And there's one thing that you don't know, and that's the frequency, and that's what we want to solve for.
So maybe we should set that up, and then we'll get our trusty calculator out.
Oh, yes.
All right.
So if you go ahead and divide both sides by lambda, just doing a little bit of simple algebra,
yeah, the lambdas
cancel out, and you're left with frequency is equal to the speed of light divided by the wavelength.
So what's the speed of light? We should try to plug that
Let's
in.
put some numbers in here. So this is 3 times 10 to the 8th meters per second. And then here we're going to use our wavelength.
5.4 there, yeah, I see.
5.4 times 10 to the minus 11 meters. And the meters divides out, and we're left with 1 over seconds, which is our friend, the hertz.
Okay,
it works.
So we should do that on the calculator.
Let's
so I've got
crunch
my
some
calculator
numbers.
on. And so I've got now 3. Now remember, I have to push second function E to get my E button.
There's that
E8. We talked about that in the last chapter. Divided by 5.4 second E. Now make sure one thing I'm not doing is I'm not pushing times 10. E, what was the number? 11? Negative 11.
Minus 11.
Negative 11. So you can see on the screen what I get. And my fancy number
Whoa.
is 5.55. Probably we're just going to say 5.6 maybe.
Well, let's just
5.6
round. Yeah.
times 10 to the 18th
Hertz. Cycles per second.
So that's the answer, guys. It's not that hard. That's pretty easy, isn't it?
That's so many cycles per second, I don't even understand it.
That's
But
it's
impressive.
It's a big number. Okay, so let's take a look at another problem. Example 1. Let's look at example 2.
Whoa.
What is the frequency of green wavelength that has a wavelength of 552 nanometers?
Whoa.
So we're going to use that same equation, right, Dr. Boyer?
Yes, we are.
F times lambda equals C.
That's right.
Now, when I was, hold on, this calculator's in there. All right, what is the frequency? So I'm going to solve for frequency, so I'm going to divide both sides by, this is the same equation, Dr. Boyer.
It is.
So I get F is equal to C over lambda, but I've got kind of a problem.
Uh-oh.
And that problem is the 552 nanometers.
What are we going to do? Oh, wait a second. I remember that thing. That's 10 to the minus 9. It's a nano. So this is going to be 552 times 10 to the minus 9 meters. Bingo.
So you can just plug
now
that in.
we can use it and plug it in. Yes, indeed.
So then I'll just say 3E8, I'll write it that way.
All right.
Divided by 552 E negative 9, right? So that's what I'm going to type into my calculator.
Let's see what that gives us.
So I've got, what, 3E8 divided by 552 E negative 9. So that nanometer is the thing that's a little bit confusing, but that's all you've got to do is just say times 10 to the minus 9th, and what do we get? 5.4 E14. By the way, when you're typing this into Moodle, by the way, when I give you a question like this, and they'll be hertz, make sure you type in the E. That's how Moodle does it. Don't say times 10 to the power.
Oh, please don't.
That's the way Moodle just works with math stuff. So, and now we believe we've got one more to do. And when that one more is example 3. So what is the wavelength? Oh, the calculator's in the way.
Oh.
So we're going a different way now. We have the frequency, but not the wavelength.
Oh,
so how would you do that one? That'd be backwards, right?
I know how to do this.
I bet you do.
Let's see, we got frequency times wavelength is the speed of light, and we're given frequency, and we want to find the wavelength. So
you
let's
divide by F, right?
Yeah, now we can get that F canceled out and we get lambda is equal to the speed of light over frequency.
Okay.
Well, let's see. Numbers? Oh, speed of light. I know
3.
that. 3 times 10 to the 8th meters per second. And then I've got to put in the frequency. 8.8 times 10 to the 14th hertz, which is 1 over seconds. Seconds goes away, and I'm left with meters. Yes! Let's do some number crunching here.
Let's bring up the trusty calculator, and I've got 3E8 divided by 8.8 E14. Oops. 3E8 divided by, I messed up guys, 8.8 E14.
14. There we go.
4. There we go. 4. So
Yeah,
this is
there it is.
3.4 times 10 to the negative 7. Or on Moodle, you'll say 3.4 E negative 7. Those are meters.
Meters. Oh, that's short. Whoa.
Okay. So, guys, that essentially is podcast 3.1. So hopefully you understand why.
All right, Mr.
See you in
Bergmann.
class.